Hi everyone, I'm Michael Herrsche from IBM Research Zurich. On behalf of my co-authors, I'm excited to present you our ICML paper on locally coherent parallel decoding in diffusion language models. Diffusion models are a promising alternative to autoregressive models. Instead of predicting one token at a time from left to right, they predict multiple tokens per step. This enables sublinear latency. Beyond speed, diffusion language models offer unique capabilities, like bidirectional modeling, infilling, or self-correction. However, parallel decoding struggles when multiple valid sequences exist under the data distribution. For example, a prompt asking for a parity function could have multiple valid solutions. This becomes problematic for masked diffusion models because the likelihood of each token is modeled as an independent conditional marginal. If we sample from these marginals independently, we can get incoherent results, like mixing one token from solution A and one from solution B. This incoherent sampling is particularly detrimental in coding, where we can break syntax. To solve this, we introduce coherent diffusion with local autoregression, or CODILA for short. CODILA delegates the sampling of local blocks to a small AR model. First, we organize the output sequence into blocks of neighboring tokens. Our theoretical analysis proves that this block-wise modeling strictly reduces the lowest achievable NELBO. But directly modeling block probabilities is computationally too expensive for large vocabularies and block sizes. So we pass the tokens through a standard diffusion transformer and feed those conditional marginal likelihoods into a local AR model. Conditioned only on this local context, the AR model generates a coherent block. Importantly, CODILA maintains the diffusion model's bidirectional context and any order generation capabilities. The key enabler here is soft conditioning. At its core, soft conditioning creates soft embeddings via a convex combination of the conditional marginal probabilities from the diffusion model and the embedding matrix of the AR model. We encapsulate these soft embeddings with begin and end of thinking boundary tokens. Given this soft context, the AR model retrieves a coherent sequence. We found that the pre-trained chain of thought model already has some knowledge for this retrieval task, and simply fine-tuning a compact 0.6b parameter model is entirely sufficient. We empirically validate CODILA on code generation, comparing pass-at-1 accuracy against batch size 1 throughput. In blue, you can see the standard dream coder instruct 7b. It can improve throughput by sampling multiple tokens per iteration, but at a notable drop in accuracy. On the other hand, CODILA in yellow samples an entire contiguous block per iteration, which lifts the accuracy during parallel sampling. The computational overhead of the small AR model is minimal and fully amortizes at larger batch sizes. Moreover, CODILA significantly outperforms other parallel sampling baselines that incur a notable overhead. Interestingly, we found that CODILA's accuracy gains can be explained by a notable improvement in syntax error rates. So, enhancing coherence during parallel sampling through our blockwise AR execution naturally enhances syntax. So far, we've looked at generating a full block per iteration, but CODILA's AR model can also perform partial block completion, allowing us to dynamically adjust parallelism based on a model confidence. This dynamic sampling is also highly effective for non-causal tasks. For instance, when integrated into DreamOn for code infilling, CODILA enables accurate parallel sampling and establishes a new Pareto frontier compared to both standalone AR models and standard diffusion models. To conclude, CODILA enables fast parallel generation in diffusion models by delegating local sampling to a lightweight, soft-conditioned AR model. This sets a new Pareto frontier for code generation while preserving the core benefits of diffusion, like bidirectional modeling and infilling. If you're interested, please check out the paper. Thank you for your interest and see you in Seoul at ICML.